Let's dive into one of the coolest, literally, puzzles in all of physics. We're going on a journey to the coldest possible temperature. This isn't a place you can visit, though. It's a fundamental limit of reality itself, absolute zero. It's kind of like the ultimate finish line for cold. But here's the twist. It's a finish line we can never, ever actually cross. So let's just start with the big, obvious question that kicks this whole thing off. I mean, we all get hot and cold, right? But is there a bottom? Is there some point where things just stop getting colder? And the answer is, yeah, a very definitive yes. And here it is, 0. Not on the Celsius or Fahrenheit scale you might be used to, but 0 on the Kelvin scale. For perspective, that's minus 273.15 Celsius, or a truly staggering minus 459.67 Fahrenheit. Now, scientists love the Kelvin scale because it's tied directly to energy. And the classical thinking was, at 0 Kelvin, everything, every atom, every molecule, which has come to a complete and total stop. No wiggling, no vibrating, just perfect, absolute stillness. But that beautiful idea of stillness, well, that's where our real story begins. Because it turns out, it's an illusion. You see, the first reason we can't get to absolute zero comes from the basic rulebook of the universe, the laws of thermodynamics. It's like we're running full speed towards our goal and we slam smack into what you could call the thermodynamic wall. These laws govern how heat and energy work, and they have some pretty strict things to say about our little quest. It really all boils down to this one concept called entropy. And don't worry, it's not that complicated. Entropy is just a fancy word for disorder or randomness. Think of your bedroom. When it's super messy, that's a high entropy state. When it's perfectly clean and organized, that's a low entropy state. So the third law of thermodynamics basically says that as you cool something down, it gets more and more orderly. Its entropy drops. And at absolute zero, it would reach a state of perfect minimum entropy. But actually reaching that state of perfect order, yeah, that's the problem. Here's why it's a problem. Trying to reach absolute zero is kind of like one of those old brain teasers, Zeno's paradox. Imagine you want to walk to a wall. First, you walk half the distance. Then you walk half of the remaining distance. Then half of that tiny distance left. You see where this is going, right? You get closer and closer, infinitely closer, but you never actually touch the wall. Cooling works just like that. Each step of a cooling process removes some heat, but it's always just a fraction of what's left. So to get rid of all the heat, you'd literally need to take an infinite number of steps. It's an impossible journey. And just to make things even harder, the very thing you're trying to cool starts to fight back against you. See, every material has something called a heat capacity, its ability to store thermal energy. But as you get a material colder and colder, its heat capacity just collapses. It becomes absolutely terrible at giving up those last little bits of heat. It's like you're trying to bail out a boat that's almost empty, but now you're only allowed to use a thimble. The work becomes incredibly exponentially harder. Okay, but let's just pretend for a second. Let's say we could somehow cheat thermodynamics and take infinite steps. Well, even then, we'd find another barrier waiting for us. And this one is even weirder. Now, we have to leave the world of classical physics and enter the bizarre, spooky realm of quantum mechanics. And at the very heart of this new problem is a fundamental rule of the cosmos, the Heisenberg uncertainty principle. It's a non-negotiable law of nature. It says there's a cosmic trade-off. The more you know about where a particle is, the less you can know about where it's going. It's momentum, and vice versa. You can never, ever know both of those things perfectly at the same time. And that one simple rule completely destroys the idea of a perfectly still particle. Okay, let's break that down, because it's a bit of a mind bender. Our old school classical idea was that at absolute zero, a particle would be perfectly still, right? That means its momentum would be exactly zero, and it would be sitting in one precise spot. But the uncertainty principle says, no way. If you knew its momentum was exactly zero, then you would have zero information about its position. It would be infinitely spread out. It could literally be anywhere in the entire universe at once. Since that's obviously not possible, our whole starting idea that a particle can be perfectly still has to be wrong. And this leads us to one of the wildest ideas in physics, something called zero-point energy. Think of it as a fundamental background hum in the universe that can never be turned off. It is the absolute minimum energy that the laws of quantum mechanics will allow anything to have. So even at the theoretical limit of absolute zero, particles will always have this tiny bit of energy, causing them to constantly jitter and vibrate forever. They can never be truly completely still. So, if we can never actually get to absolute zero, you might be asking, well, why even bother trying? That's a great question. And the answer is because the chase itself, getting as ridiculously close as we possibly can, has unlocked some of the most amazing and revolutionary science in modern history. I mean, the machines scientists have built for this are just mind-boggling. We're talking about dilution refrigerators that use super rare types of helium, incredibly powerful magnets designed to literally squeeze the heat out of atoms. And my personal favorite, laser cooling. Scientists use lasers to create what they call optical molasses. They actually use photons of light to physically grab onto atoms and slow them down to an absolute crawl. With these techniques, we can now reach temperatures that are just billionths of a degree above absolute zero. It's just insane. And the things we've found down there in the ultra-cold? Whoa, we discovered superconductivity, materials that can carry electricity with absolutely zero resistance, a perfect conductor. We found superfluids, liquids that flow forever without any friction. We've even created a whole new state of matter called a Bose-Einstein condensate, where thousands of individual atoms basically merge and start behaving like a single giant superatom. And all of this work, it's the foundation for building the next generation of world-changing quantum computers. So when we pull back and look at the big picture, we see that absolute zero isn't some kind of failure on our part. It's a perfect, fundamental boundary that helps define how our universe works. It's not a destination we're supposed to arrive at. It's a fixed point on the horizon, forever shaping the laws of reality as we know it. So let's just lay out the final verdict. Who are the two culprits stopping us from reaching absolute zero? Culprit number one is thermodynamics. It tells us that reaching zero is an infinite journey of smaller and smaller steps, which is impossible. And culprit number two is quantum mechanics. It guarantees that every particle has a minimum zero-point energy, so nothing can ever truly stop moving. It's a definite 1-2 punch from the fundamental laws of physics. Case closed. And that leaves us with a really fascinating thought to end on. Absolute zero is one of the universe's great unbreakable speed limits, just like the speed of light is the ultimate speed limit for motion. It really makes you wonder, doesn't it? What other fundamental boundaries are out there, quietly shaping the fabric of our reality? It's just a powerful reminder that sometimes the biggest truths in science aren't about what we can do, but about understanding the beautiful, elegant limits of what's even possible.